In this lesson, we're going to learn about algebraic vectors and the dot product. But let's first talk about standard position. A vector is in standard position if its initial point is located at the origin. We often represent these vectors with a single letter and the following notation. A, there's an arrow over top of that A, so you can have any letter really, but the arrow over top indicates that you're dealing with a vector. And then I have my components x and y inside a set of, they're almost like greater than, less than symbols that are extended, but straight brackets basically. The magnitude and direction can be expressed as the magnitude of vector A is the square root of x squared plus y squared, and the tangent of the direction is y over x. Or you can write that as theta equals the arctangent of y over x. Find the magnitude and direction of vector A, which is 6, 8, then sketch the vector. The magnitude of vector A is going to be the square root of the x component squared, so the square root of 6 squared, plus the y component squared. In this case, that would be the square root of 36 plus 64, or the square root of 100, which is 10. So the length of this vector is 10. The direction is going to be the arctangent of y over x, so 8 over 6, and I'll get the calculator to determine what that is. So make sure I'm in degree mode, because I'm going to answer with degrees. So the arctangent, of 8 divided by 6, you don't have to reduce it, it'll take care of that. So 53.1 degrees. Now to draw a sketch, I'll just sketch on here. The x component is 6, so I'd go over 1, 2, 3, 4, 5, 6, and then up 8. 1, 2, 3, 4, 5, 6, 7, 8. And wherever those meet, that's the end point of my vector. And I'll draw it in with an arrow and label it vector A. And a lot of times when you are writing vector A, usually a symbol like this is used rather than drawing a double-sided arrow, just for time constraints. So that's just one thing to make sure you're aware of. Horizontal and vertical components. A vector can be expressed using a magnitude and direction, and if we wanted to calculate the horizontal and vertical components, we could do so using the following formulas based on right triangle trigonometry. So if I have some vector u with an endpoint xy, then I can define the value of x as the magnitude of u times the cosine of angle theta, and y as the magnitude of u times the sine of theta. So there's always this strict relationship between the x and y components of the vector and the magnitude and the direction. So you can go either direction. An example: express the vector whose magnitude is 8 newtons in the direction of 68 degrees in component form. So we have some vector u whose magnitude is 8 newtons, and the direction of that vector is 68 degrees. So the x and y components come from taking the magnitude of the vector and multiplying by the cosine for the x direction of that angle measure and the sine of that angle measure for the y. So in this particular case, x is going to be 8 cosine 68 degrees, and y will be 8 sine 68 degrees. And I'm just going to round things to one decimal place for simplicity, but I'll need to do this on the calculator. So 8 cosine 68 degrees and 8 sine 68 degrees. We get approximately 3.0 and 7.4. So vector u could be expressed as 3.0 comma 7.4. Vector operations. Vector addition. The sum of two vectors, u equals ab and v equals cd, is performed as follows. We just add their individual components. Interestingly, this has the same geometric interpretation as we learned in the last lesson, the diagonal of a parallelogram, that is. Scalar multiplication, if the vector u equals ab is to be multiplied by the scalar value k, then the result is k times component a plus, or comma, k times component b. And the operation here only affects the length of the vector and it does not change its direction. So in the same way that it did geometrically in the last lesson. So let's look at an applet for scalar multiplication and vector addition and see how that works. So for scalar multiplication, I have an initial vector that has the coordinate pair 1, 3. That's the endpoint. That's vector u, and defined by the point P. And just assume that it's in standard position here. The next vector is 2 times u, and if you'll notice, it's in the same direction, and it has the endpoints 2, 6. So I've effectively just multiplied 1 and 3 by 2. 1/2 of u is in the same direction, it's just half the length, and its coordinates are 0.5 and 1.5. And negative u is the same length but in the opposite direction. And no matter where you move the point P, that same relationship always holds. 2u is always the double the length of vector u, but still in the same direction. Same thing for 1/2 u. It's always half the length, just in the same direction. And then negative u is opposite in direction, but simply but the same length. So scalar multiplication only affects the length of the vector and not its direction. For vector addition, if I have two vectors, u as 1, 3 and v as 5, 1. If I add their individual components, that would be 6, 4. And when you plot that, it becomes the diagonal of that parallelogram drawn between the original two vectors. And no matter where you move the endpoint of vector u or the endpoint of vector v, that relationship always holds. So the geometric interpretation of adding vectors is the same as the algebraic interpretation of adding vectors. So use the vectors u equals -2, 5 and v equals 3, 6 to answer the following. Sketch each vector and the resultant on the graph provided. So I want to do vector u plus v. So u plus v would be evaluated by taking the x components of each vector and adding them, and the y components of each vector and adding them. So we would end up with 1, 11. Now I want to sketch these. So when I sketch these, vector u is -2, 5. So -2, 5 would be about right here. So there's vector u. Vector v is 3, 6. So 3, 6 would be approximately right there. Now, if I create a parallelogram, and I do it as accurately as I can, which I can't promise that it's going to be extremely accurate. I think I'm actually pretty far off. Well, let's see what happens. So 111 would actually be right here. So 111 would be up here. Tell you what, let me erase these lines. Alright, so that's what's supposed to happen with the parallelogram. Okay, so I needed to be a little bit more accurate in my drawing, but it's always going to work out that way. That's what I want to show. Okay, next up, let's do 3/2 of vector v. So vector v, it was the components 3, 6. So 3/2 of v is going to be 3/2 of 3, 6. 3/2 of 3, that's going to be 9/2. And 3/2 of 6, 6 divided by 2 would be 3. 3 times 3 is 9. Okay, so let's sketch these. So the original vector, vector v, 3, 6, is approximately right there. Now if I draw 3/2 of v, it's at 9/2 and 9. 9/2 is approximately 4.5. So 4.5 and 9 would be about right there. If I draw a vector to it, it's pretty well right on top of the original vector. So it's in the same direction, but just a longer length. And that length has been increased by basically half. Right, 2u minus v. So this would be the same as 2 times the vector u, which is -2, 5, minus vector v, which is 3, 6. So when I multiply, this becomes -4, 10. I'm just multiplying each component by 2, minus 3, 6. And now I'm going to subtract the individual components. So -4 minus 3 is -7. 10 minus 6 is 4. When I sketch these, let me show you what happens. So the original vector u is at -2, 5. So approximately right there. Then v is at 3, 6. Okay. Now, in green, I'm going to first multiply vector u by 2. So that's at -4, 10. Okay. And then in green, I'm going to put the negative of vector v. So -3, -6. So -3, -6 should be about right there. So same direction, just opposite, just pointed opposite. Now in red, I'm going to do the resultant. So -7, 4. So -7, +4 is going to be about right there. And let's see what happens in terms of parallelogram rule. So if I draw a parallelogram around these resultants, it seems to work out pretty well. So again, forgive me of my accuracy of the drawing, but it will all work out if you take the time to be very accurate. So that's how these all work out. I and j notation. Another common method of expressing the endpoints of a vector is to use the ij notation. I and j are defined as unit vectors, which have length 1, along the x and y axis respectively. So I is 1, 0, j is 0, 1. So if I call this point 1 like that, so I just kind of increase the scale a little bit, then vector I, which is 1, 0, would be this. And sometimes you'll see instructors write I like this. Sometimes they stick with the notation with the arrow on top. It's really kind of up to the instructor how they tend to prefer it. These are my representations of I and j, so just so you know how I'm writing it. Using these unit vectors, it's possible to express any vector in component notation or ij notation. And it really comes down to the textbook that you're using. One thing that I do notice is a lot of physics textbooks tend to prefer using the ij notation, whereas mathematics textbooks tend to prefer the component notation. It doesn't really make any difference because they're both completely interchangeable. So for instance, if I have vector u in component notation, what I can do is take vector u and express it as 3, 0 plus 0, -5. So I can split it up into the x and y components and make it two separate vectors. That's completely fine because when I add these two together, we end up right back to the original vector. Then I can factor out from each one of these the common factor. And now substituting in I and j for the remaining vectors, I have 3i minus 5j. And so that's the exact same representation, or the exact same vector, just a different representation of it. So you can use the ij or you can use the component. It's up to you. The dot product. Given two vectors u equals ab and v equals cd, the dot product between these two vectors is u dot v is ac plus bd. Note that the result of the dot product operation is a scalar value, not a vector. Let's calculate the following dot products. So first, the dot product of -5, 1 dot 3, 2. So it's pretty straightforward. We just take -5 times 3 plus 1 times 2. So we just take component by component, multiplying them. So -15 plus 2, which is -13. And that's the result of the dot product. You might be wondering, why would we define vector multiplication in this respect rather than just saying, all right, for vector multiplication, just multiply the components and leave it as a vector? Well, it turns out it really comes down to applications. There's many more applications of a dot product than a product in that respect, where you leave it as a vector. There's actually another type of product that we use for vectors, which is seemingly even more strange when you first see it, but it has more applications, and that's the reason why we choose to use it. Okay, next up, 10, -2 dot -1, -4. So 10 times -1 is -10. -2 times -4 is 8. So the result of that dot product is -2. -3, 5 dot -3, 5. So -3 times -3 is 9. 5 times 5 is 25. Notice we've just basically squared each component here when taking the dot product with respect to itself. When we add these together, that is 34. 0, 0 dot 2, negative 24. 0 times 2 is 0. 0 times negative 24 is 0. So the result of the dot product with the 0 vector is the value 0. And let me sum up some of these situations with some properties of the dot product. First, the dot product can be reversed. U dot v is the same thing as v dot u. And that's easily seen, if you just let u equal ab and v equal cd. So if you take u dot v versus v dot u, well, u dot v would be ac plus bd. V dot u would be ca plus db. And since multiplication and addition both can be turned around in that respect, dot product works that way as well. Next up is like a distributive property. U dot the sum v plus w is u dot v plus u dot w. K times the dot product u dot v can be done by applying the constant value k to either vector first. So it doesn't matter if you do it before the vector operation or after the vector operation. It's either way is fine. The 0 vector times any vector is equal to 0. I'm sorry, the 0 vector dot any vector is 0, the number 0. Note the difference between the 0 vector and 0. These two things are not equal to one another. They're two separate concepts. And finally, u dot u is equal to the magnitude of u squared, which is kind of what we showed in an example earlier. Now, one of the main applications of the dot product is finding the angle between two vectors. So let's see how that happens. But given any two vectors, u and v, we can find the angle between those two vectors using the dot product in this formula. Cosine theta is u dot v divided by the magnitude of u times the magnitude of v. And I think it's instructive to see a proof of this, so let's walk through it. We need to come up with an initial setup here to work with, and I have vector u and I have vector v and the subtraction between those two. Now, I'm looking for this angle measure right here, which I will call theta. And if you'll notice, I've set up a triangle, which is non-right, but I know the sides of this triangle, and I'm just looking for the angle measure itself. So I can use the law of cosines here. So basically, the law of cosine says to take the length of the side that is opposite your angle that you're interested in, square it, and that's equal to the length of the remaining two sides added together, squared that is, minus 2 times, in this case, magnitude u, magnitude v, cosine of the angle between them. Now, effectively, the only thing that would be unknown here would be the angle measure, and you could always use the law of cosines to solve this. But it's much easier if we work with this a little bit algebraically and rewrite this in a more easier way. Now, the property that we have to work with is that the magnitude of u times itself, or dot itself, sorry, vector u dot itself is equal to the magnitude of u squared. So we have a lot of magnitudes of vectors squared. We're going to turn those into dot products with themselves. So for instance, on the left-hand side, I can express this as u minus v dot u minus v. And then I can express u squared, the magnitude of u squared, as u dot u. And the magnitude of v can be expressed as v dot v. And I'll leave this part alone for just a moment. I'll get to it in a bit. So cosine theta. All right, now the next step, because I have binomials, so two vectors that are subtracted in this case, and I'm taking the dot product between them. There's another another property that says that we have a distributive property with vectors. And because we have a distributive property, that it inherently implies that we also have FOIL. So I can FOIL these vectors out. So if I take the first two and multiply them, well, dot product them, I suppose I should say, it would be u dot u. The outer two would be minus uv, u dot v. The inner two would be minus v dot u, and the last two would be plus v dot v. And then I'll recopy this part on the right hand side for now. Okay, next is, if you'll notice, we have u dot u on both sides. So no matter what that is going to turn out to be, it's going to be the same on both sides. You could subtract it and cancel it. Same thing with v dot v. Those will just simply cancel. These two remaining terms, u dot v and v dot u, they're the same value as well, because you can turn around the dot product. That was another property that we saw. So I could write these two terms as negative 2 u dot v, and that's going to be equal to negative 2 magnitude u magnitude v cosine theta, which if you divide both sides by negative 2, you'll see those negative 2's cancel, and we now have u dot v equals the magnitude of u times the magnitude v cosine theta. And if we just divide both sides by the magnitude of u times the magnitude of v, we arrive at our formula. And there we have the proof. Okay, so let's use that formula. Let's find the angle between the vectors u equals 2, negative 3, and v equals 1, 5. So the cosine of the angle between two vectors is u dot v over the magnitude of u times the magnitude of v. So let's get started finding some magnitudes. So the magnitude of u is going to be the square root of its x component squared plus its y component squared, so root 13. The magnitude of v is going to be its x component squared plus its y component squared, so square root of 26. So the cosine of the angle measure, u dot v, well, I'll work this out before I get started. So u dot v would be 2 times 1 plus negative 3 times 5, so negative 13. So negative 13, whoops, sorry, negative 13 divided by the square root of 13 times the square root of 26. And generally, we'll just need to throw this into the calculator. So I will do that. And I'm going to be doing the arc cosine of negative 13 divided by the square root of 13. Oh, you know what? I need to put some extra parentheses in the denominator for the order of operations. Times the square root of 26. Oh, well, that's interesting. We got an exact angle measure. So theta equals 135 degrees. That's going to happen pretty rarely. Usually it's going to be a decimal that goes on forever. Okay. Using this rule, we can infer the following important relationships between any two vectors. So the sign of the dot product, it can turn out to be either positive, 0, or negative. And if that's the case, that says something about the type of angle that's formed. If the dot product is positive, we end up with an acute angle in between the two vectors. If the dot product is 0, we end up with a right angle. And if the dot product is negative, we end up with an obtuse angle. And really the most important relationship is right here. So if the dot product is 0, you have a right angle. But let's check out and see what type of angle exists between the vectors u equals 1, -5, and v equals 5, 1. So we calculate the dot product. So u dot v would be 1 times 5, which is 5, plus -5 times 1, so that's -5, which is 0. So there's a right angle between these two vectors. How does the slope of these two vectors relate? Well, the slope of these two vectors, the slope of vector u, I'll just say mu, is going to be the -5 over 1, and the slope of vector v is just going to be, again, y over x, so 1/5. And if you'll recall, back from, say, Algebra 1, for instance, you learned a rule that said how two vectors were related if their slopes were, not vectors, you didn't learn about vectors, but two slopes were related if they were inverses and negatives of one another's. So these are negative inverses of each other. And what you learned about that is that those types of slopes were perpendicular to one another. And if they're perpendicular, they meet at a right angle. So that's actually where that law came from, is through the study of vectors.